Today we will talk about nucleophilic substitution reactions. If you recall from your days of general chemistry, you may remember about double displacement reactions in which two ionic salts are combined with each other, you swap the anions, and you end up with new ionic substances as products. And in a way, this type of reaction is very similar to the reaction that we're going to talk about today. Um, Just a little reminder, when you're doing these double displacement reactions, there is no change in the charges of the species. Now, in organic chemistry, typically one of the types of reactions that you can um, perform is that of addition of an ionic molecule to an organic molecule. And in this setup, instead of having two ionic substances, now you have a covalent substance in combination with an ionic substance, but the organic molecule bears a weak bond. And this is not to be confused with the homolytic cleavage um, that we talked about in the radical chapter, but rather this is a weak bond in the sense that it can heterolytically cleave. So the electrons will go completely to one element. The second element will be left without the electrons that it used to share through that bond. And in doing so, it will exchange the anionic groups. So you will end up producing a new organic product, but then you'll also have a byproduct salt that you'll have to separate from your organic product. The reactant that technically is the ionic component is composed of a regular cation, and the anionic portion of that ionic salt is what we call the nucleophile. And this is very specific of organic reactions. A nucleophile means that you are attracted to positively charged species like a carbon that is connected to an electronegative element like a halogen. In that situation, the carbon will develop a delta plus, which will be sufficient enough to attract the nucleophile to it. The organic molecule also has a term of its own. The carbon that is being attacked by the nucleophile is known as the electrophile. And electrophile basically means that you have an atom that is very much attracted to negative charge. And the anionic component of the organic molecule is known as the leaving group. This is what has to take off in order for the substitution to occur. And pretty much what you're seeing right here is that the organic product starts with a particular anionic component and ends up with a different one, like your typical double displacement reaction. Now, what a typical nucleophile may look like is a metal salt. So you can have a metal combined with your anion. You could even have an acidic substance, and you could even have some other organic substance, except that for these neutral covalent molecules, you have to have lone pairs present in order for them to become nucleophiles. In regards to the metal anionic species, the metal bears the positive charge, the anion bears the negative charge. And typically speaking, the metals that are often used are those in groups 1, 2, and 3 of the periodic table, most commonly being groups 1. And there's one more possibility, and that possibility is that you have no metal associated with Y, in which case Y is neutral. The only prerequisite, though, is that Y contain lone pairs in order to act as a nucleophile. Now, on the other hand, the organic molecule, the starting organic molecule in your reaction is going to have that electronegative bond, um, either to a halogen or some other species that is more electronegative than carbon. And what I was implying before is that even though you are developing the delta pluses and delta minuses, and this makes this bond stronger, it makes it stronger from the point of view of homolytically cleaving the bond. But when you're talking about kicking out this X group with the two electrons that make up that bond, you're not really breaking this homolytically, but rather you're breaking it heterolytically. And in that scenario, this discrepancy of charges makes it so that this carbon is more reactive. All right, so keep that in mind, and the fact that this carbon is going to develop a delta plus on it as a result of being bound to this electronegative group. All right, and just to kind of drive the concept forward, nucleophile stands for loving positive charge, electrophile stands for loving negative charge. In essence, they want to be associated with each other. Okay, so let me show you a few examples to kind of set the scene right here. On the left side, you have your reactants, and of course, you have your products on the right side of this equation. And what you will notice is that out of the two reactants, one of them is composed of a metal. And what that's telling you is that this metal salt must be the nucleophile. In particular, the anionic component, which is this sulfur combined with a methyl group, is the nucleophile. And what that means is that the second reactant must be the organic molecule. Specifically, the electronegative group, the chlorine, must be the leaving group. And the carbon to which the leaving group is bound is the electrophile. Altogether, electrophile plus leaving group is also referred to as the substrate. So here on the product side, you have your byproduct salt, which is fully inorganic. And you have, of course, your organic products, the one where you have exchanged and substituted your chloro group for a thio group. Another way in which you can undergo this substitution reaction is by having a neutral covalent molecule like water. In this case, you can react the two molecules together and undergo an exchange, and the organic molecule still has to be the substrate, meaning that the carbon over here directly bound to chlorine must be the electrophile, and the chlorine is the leaving group. That means that the oxygen that has lone pairs is going to be your nucleophile. And notice what's happening right here. If you write water in basically the same way in which I have done right here, then technically speaking, the H is behaving as the cationic version of water, and the OH is the anionic. In other words, this is hydronium and hydroxide, right? So when you do the exchange of the chloro group is going to be with a hydroxide, and the chloro group will now be associated with the H plus. And in essence, that's what we have right here. We have formed hydrogen chloride and a new alcohol. So those are the byproducts, and this is the product. And of course, the byproduct here is not an ionic substance, but rather a binary acid. One that, if you don't have much water around, aside from the one equivalent that you're using for the reaction, then it will basically come off as a gas. But if you have enough water present, then this is going to dissolve in water and give you hydrochloric acid. Okay, one more example. You have here another organic molecule reacting with a second organic molecule. Now the thing to recognize is which one of the carbons in the reactant side is bound to an electronegative element. And if it so happens that both of them are, then the question becomes, well, which one is the more electronegative element out of them? And bromine turns out to be a little bit more electronegative, or at least a little bit more willing to break up from this carbon halogen bond than sulfur would be. And we're going to get into the details as to why ultimately that happens in just a little bit. But what this basically means is that the molecule here without bromine or halogen is going to be altogether the substrate. The halogen is the leaving group, and the carbon to which the halogen is bound is the electrophile. So what this means is that the sulfur, where you actually have lone pairs, is going to act as the nucleophile. And once more, this H, which is less electronegative than sulfur, is going to behave as the cationic component. So you'll end up exchanging this H plus for the isopropyl group and forming HBr in the process, as well as a thioether component. Okay, so a few more things to emphasize in this video. We need to describe what a nucleophile is and what a leaving group is. All right, so nucleophiles. Some of the common ones are presented right here, and these are the strong nucleophiles. We have phosphorus containing compounds that are actually organic. So these R groups are organic, and then this is phosphorus. This is known as a phosphine. Then you also have um, HS, or this could be RS minus. These are thiolates. Down here you have cyanides, iodide, amines. Whether they have hydrogens or not, they still kind of work the same way. So you have amines, and then at the end of the series you have um, alkoxides and hydroxides, and the alkoxides and hydroxides are um, not as good nucleophiles as your phosphines, thiolates, or cyanides. Then you have the moderate nucleophiles, bromide, ammonia, neutral thioethers, chloride, acetate. And then the moderate to weak ones, you have fluoride, alcohol, water. All right, so the thing to keep in mind right here, or at least the thing to notice, is that regardless of whether the substance is charged or not, the thing that they all have in common is that they have lone pairs. And those lone pairs are key to attack an electrophile. Now, when you look at the trends on the table right here of nucleophilicity, sometimes the basicity trend goes in line with nucleophilicity. Case in point, if you look at the alkoxide or the hydroxide, they are strong nucleophiles in comparison to the alcohol or water molecules from which they are derived. So you have the stronger base, the stronger conjugate base of the duet being the stronger nucleophile. But the truth of the matter is that most of the time, basicity doesn't really equate to nucleophilicity. The time when it does is when the elements are roughly of the same kind, or the rest of the molecule is exactly the same. In that case, the basicity argument works really well in terms of determining what's more nucleophilic. But generally speaking, the nucleophilicity increases as you approach electronegative values close to carbon. Um, and so if you look at the periodic table, and this is only the P block of the periodic table and only a selected sample of it, going towards carbon is going to get you closer to the electronegativity of carbon. Uh, but you could continue decreasing that electronegativity. And so you could actually, if you follow the trend of the periodic table, that electronegativity decreases going from right to left, and it also decreases going from top to bottom. So what this basically means is that fluorine is going to be less nucleophilic than oxygen. Oxygen is going to be less nucleophilic than nitrogen. Nitrogen is going to be less nucleophilic than carbon. Phosphorus is going to be more nucleophilic than nitrogen. Sulfur will be more nucleophilic than oxygen, and so on and so forth. By and large, the elements that we're going to be looking, by far are the following five that are highlighted here: carbon, nitrogen, oxygen, phosphorus, sulfur, and, well, of course, the halogens, right? So the ones that bear the more nucleophilicity, and you can see here the strong nucleophiles contain phosphorus as the source of the electrons, sulfur, carbon, iodine, nitrogen, and even oxygen. So you can see them all here. These are the ones that make up the strong nucleophiles, and they, generally speaking, have this trend that they are closer to carbon, going from right to left, or they are farther down in the series, like iodine. So that's just to give you a general idea, because truth be told, when you read this trend of nucleophilicity in textbooks, it's very ambiguous. And I think the reason why is because they make a big point of trying to equate the basicity to nucleophilicity, and then a few pages down the line they tell you, oh well, technically doesn't work. So it tends to confuse a lot of people. But if you look at it from this point of view, the idea that decrease the electronegativity of the element gives you a better nucleophile, then you can see that, well, yeah, iodine is less electronegative than bromine, chlorine, or fluorine, so it's going to behave as a better nucleophile than the other halogens. Although, as you'll see a little later, it depends on the conditions at hand too. Sulfur is going to behave as a better nucleophile than oxygen. Phosphorus is going to behave as a better nucleophile than nitrogen. And generally, that's what you see right here, because the nucleophilicity decreases going down in this column. All right, now the living group. The living group also has a nice little story. And in essence, it is through the living group that I recognize what molecule is the substrate on the reactant side. The idea is that a good living group is one that derives from a strong acid. And the idea is that the living group is the conjugate base of the acid. So if you look at the strong acids, HI, sulfuric acid, HBr, HCl, tosylic acid, protonated ether, protonated carbonyls, protonated alcohols, protonated water, aka hydronium, or nitric acid. These are all strong acids, and we know that because the pKa's are all negative. This is very much indicative of strong acid behavior. So the conjugate bases of strong acids are substances that we regard as being either non-basic or very, very weakly basic, if at all, really. And notice really what we have here. We have iodide, we have hydrogen sulfate, we have bromide, chloride, tosylate, we have just the regular alcohol, water, nitrate. All of those things make up good living groups because they derive from strong conjugate acids. All right, so now when you look at the list, at the actual list that I've told you to memorize from the previous lecture of acid-base chemistry, all the strong acids are located above carboxylic acids, right? So everything up here is going to be with negative pKa's and be a strong acid. Those are the things that give you good living groups. Now, on the other hand, as you go further down on the table and the pKa starts getting higher and higher in value, what you end up generating is moderate to bad and eventually horrible living groups. So another way to put it is that substances that have pKa's greater than water. So now we're looking at the acids. So acids that have pKa's greater than that of water are considered not acidic, right? So alcohols are not particularly acidic. Alkynes are not considered to be acidic from the point of view of water. Same thing with dihydrogen, ammonia, alkenes, alkanes, not acidic from the point of view of water. And so the conjugate bases of these pretty much non-acids are going to be not only terrible living groups, but they are really strong bases. Hydroxide is already a strong base, but then you get all the way down to deprotonated alkanes, and you're talking about some really powerful bases, really strong bases. In some cases, if you're not careful, these things can be pyrophoric and catch on fire on, just by standing on air. All right, so that's the big premise. The living group is going to derive from that strong conjugate acid. So when you look at this thing, you can see, well, sulfur is one of those elements that is below the second row, so it has a little less electronegativity, and it's a good nucleophile. Definitely falls under the list of good nucleophiles. Bromo derives from a strong acid, HBr, so that is your living group. And the moment you identify your living group, you know that this whole molecule must be the substrate, and if this is the substrate, then this right here must be the nucleophile. So this is how you go about identifying all these things. The other aspect too is that if you look at HS, the conjugate acid of it is H2S, which is a weak acid. So this, could be a potential nucleophile, right? But definitely not a living group because you need a strong acid as the conjugate acid for this to be a living group. And one more thing I'll point out is that when you start with a substance like, let's say, an alcohol is not a strong acid, and so the alkoxide by default is not a good living group, but you can turn it into a good living group by adding an acid to it. If you protonate your alcohol you end up with this protonated alcohol, which is in and of itself a strong um, acid, and so this can actually yield a good Libin group. And the way you make that happen is by using strong acids. You can add hydrochloric acid, hydroiodic acid, hydrobromic acid, sulfuric acid to an alcohol in order to turn it into a good Libin group. And we're going to look at situations like that a little later in this lecture series. So we're going to use those strong acids to turn bad Libin groups into good ones. And here I'm just going to give you one example before we end this video. Here we have an ether molecule. We're going to add a strong acid, HBr. And what happens is that the lone pairs of the oxygen, which are technically the nucleophilic portion, although in this case, technically this is not acting nucleophilically, is acting as a base. And the way you know is because it's not attacking carbon, it's going to attack the hydrogen or the proton. So this attacks the proton, the electrons go towards the bromine, and you form your protonated ether. Looking at the pKa's, the pKa of HBr is -9, the pKa of your protonated ether is roughly -4. Subtracting those values from each other gives you a value of -5. And because that value is negative, we know that this reaction is going to happen. It will take place. And in essence, you will never be able to find solutions of hydrobromic acid in ether solvent because it reacts with ether and ultimately destroys ether, unfortunately. So this is product favor. All right, so as I was saying, you could take your substance, you could take your alcohol and turn it into a protonated alcohol, and by doing so, make this a good Libin group. Or you could turn your ether into a good Libin group by protonating it, and this will be used and done with the strong acids above here. So we'll look into that a little bit later. Right, so alcohol, same idea. The O with the lone pair attacks the strong acid, takes that proton, kicks off the chlorine. In the process, you form protonated alcohol. And notice that the pKa of HCl is -7, that of the protonated alcohol is about -2.5. Subtract these two values from each other in that order, you get a negative value, which tells you that this reaction is product favor. All right, so definitely can do this. And the other method to make a bad Libin group, like an alcohol or an alkoxide, into a good one is to use this substance right here known as tosylic acid. Except that instead of starting with tosylic acid, we start with tosylic chloride or tosyl chloride. And what happens here is that the alcohol exchanges with the chloro group, and you form this new functionality, which is basically a derivative of sulfuric acid, an alkyl sulfate derivative. In this particular case, this is methyl tosylate. And the mechanism for such a reaction is as follows. Your alcohol attacks the sulfur center. The sulfur oxygen double bond breaks initially. This is called an addition reaction. Then the lone pair that you just created on the oxygen comes back down onto the sulfur, meanwhile kicking this chloro group that was there to begin with. This is called the elimination step. And what happens now is that the chloride that you generated right here comes back around and removes the proton of that alcohol. And the reason now you can remove that proton is because the moment you bound it to sulfur, the oxygen becomes an oxonium cation. And that presence of positive charge makes it likely for the proton to be removed. That's creating the tosylate. And these guys are definitely good Libin groups. This one is methyl tosylate if the group right here is a methyl tosylate if you have the benzene ring with a methyl in the opposite direction. Okay, in the next video we're going to talk about bimolecular substitution reactions, and furthermore we'll talk about unimolecular nucleophilic substitution reactions. So see you then.